A little bit about me. I'm the person who, you may have heard of me. If you have heard of me, it may be because of a couple of books I've written. This book was the one that is the one that taught me about the Stream API, because I didn't know much about it before I started writing. But writing a book is a really good way of learning about something. It's this book, and I'm pleased to say that I got given a copy by the publishers to use as a prize in a talk at Java 1, which I didn't take advantage of. So it's a prize for today's talk, if you get a question right. And I'm a Java champion, and I'm a Java rock star, doing quite well at that. So here's the agenda. This is the first half of the talk. I'm going to explain why we want collectors and what the difference is between collection and reduction. If you come across reduction, this classic idea of reduction in functional programming, and I'll explain there's a little wrinkle in the collectors API, which is quite, well, in the Stream API, which is quite puzzling, and people often fall foul of it, and so I'm going to explain what the problem is with that. And then I'll talk, most of the talk is about the predefined collectors that are supplied in the platform library. After lunch we've got work problems, and a short section at the end about writing your own, and a bit of a wrap-up. So, the life of a stream element. A stream element is born as a splitterator. It goes through some intermediate operations, and then at the end, something's got to happen to it. So in the usual way of things, I would say in functional programming, where the idea of streams came from in the first place, this isn't very problematic, because what you do is, what happens with this big question mark is that there's some way of combining the elements that have come through the stream and putting them together. They're typically, in functional programming, they're immutable elements, and so we build something new out of them. And we're going to see that doesn't work very well in Java, because Java's got a different assumption. Java's not a functional language and not likely to be one. I'm going to concentrate on what goes into that question mark at the end here. So I'm going to assume, I'm not going to talk about splitterators in this talk, how streams begin. I'm not going to talk very much about intermediate operations, because those are quite easy to grasp. This is things like filter and map and so forth. We'll use those, but I'm not going to talk about them. And of course, splitterators, we rarely have to see splitterators, because usually what we just call the stream method on list, typically, or on some other collection, and that gets us launched into a stream. So I'm really interested in this talk about what happens at the end. Terminal operations, the things that happen at the end, there's three kinds of them. There's search operations, there's side-effecting operations, and there's reductions. And again, I'm not actually going to talk very much about search operations or side-effecting operations, because they aren't so important. Generally, the model for what we want to do with stream processing in Java is typically the mainstream case is we get values out of a collection, we do stuff with them, and typically we dump them in the end back into another collection. There are lots of other things you can do with streams, but that's the mainstream case around which the whole thing was designed. And the overall objective is that bulk operations on collections we're going to replace iteration as the principal way of doing bulk operations on collections, bulk processing on collections. It's going to be replaced by streams, and that's where we're heading to. So I've got a tiny example domain for this talk, which is just a person class, which has got a person has three properties: a city, which is an enum, a name, which is a string, and an age, which is an int. And I've just done this in order so that we've got a reference values, reference components to a person, and also we've got a primitive one as well. And we would make a new person with a constructor like that, which we'll never need to do in this talk. And we're going to assume, the only thing we're really going to assume is there are accessors, there are getter methods for each one of these properties. And the other assumption I'm going to make is that we've got a list of person objects, which is going to have some sample person objects in it. So I'm going to quickly get the search operations and the side effecting operations out of the way before I get on to talking about what I'm really interested in here, which are reductions. The search operations are all match and any match, and these allow you to and find any and find first. These are typically they're interesting because they're short circuit operations. As soon as, for example, if you use find any, for example, or find first, then a stream will be processed until the value is found, and then that value is then returned, and at that point processing the stream stops. That's interesting because the way that streams work, the model is that I've lost my picture. Where's it gone? Hang on. So the model, the way that what's the matter with me here? Right. So the way that streams work is that the terminal operation here is all the intermediate operations are all lazy, and the split operator is lazy. The terminal operation is the eager thing. So it's not until the terminal operation begins that values are, the way you can think of it is values are pulled down the stream. Or in this case, what we have here is a picture of parallel streams, but the model's the same for sequential streams. So it's the execution, the terminal operation, which pulls values down. So the terminal operation has, if you like, control over what happens, and that's what makes it interesting in terms of the short circuiting operations, because, as for example, taking this one here. All match will evaluate this predicate here. So for each person value coming down the stream, this terminal operation all match will evaluate the predicate. It'll see whether or not the age of the person of each person object in turn is greater than or equal to 21. And if it finds one that isn't greater than or equal to 21, then it doesn't need to do any further evaluation. So at that point, because it's going to return false, obviously, and at that point, the processing of the stream can stop completely. If generating the elements is expensive, and if the intermediate operations are expensive, then clearly not carrying on doing them because you've got a conclusion is a useful way of saving work. So these short circuit operations are also they're useful for that, and they're also useful for infinite streams as well, because we've got generators which will allow us to create infinite streams, and obviously they're not going to be useful because we can't compute them to completion without short circuit operations like these. But so these are very useful, but they're not really what I want to talk about today. Here's side effecting operations, which I do want to talk about briefly to really give you a warning about the use of them. Side effecting operations are the first thing that people come across quite often when they first hit streams, and they find that you can do something like this, which is quite a useful thing to be able to do. You can take every element from a stream, and you can say for each. Then what I want to do is that you have here what's called a consumer. I want to supply them to a consumer. And a consumer is just something which will take a value and do something with it and not return anything. So the print line method of system works entirely by side effect. And that's what a consumer does. It just swallows a value up. So people understand this because it's like iteration. And quite often you get the question, and I think I see this question asked, for example, or I used to see it asked a lot on Stack Overflow, and I've got by far the biggest score I've got on Stack Overflow is answering the question about how would you, for example, calculate total ages. It's something related to that, and the question is, of course, why can I do this? It seems a reasonable thing to do. What we're used to doing is to declare a variable that's going to be used as an accumulator, and iteratively for each element that comes down the stream, I want to supply it to this consumer here. So this takes a value and it works by side effect. It just adds something to the accumulator variable, and then it doesn't return a value. So that seems like a kind of reasonable thing to do. And in fact, there's an argument for saying that they might have actually not put that terminal operation for each into the Stream API because it's really so deceptive. So the whole idea, if you were at the keynote yesterday, you'll have heard me going through a kind of standard sermon that I give about how the whole idea of the Stream API is to avoid iteration. This is actually an iterative model. The thing that makes this really quite a bad idea, there are a number of reasons why this is a bad idea. First of all, if you can't do it. Well, you can't do it as it stands here, because in the rules for lambdas are that that variables that you're going to assign to have to local variables that are used within a lambda rather have to be what's called effectively final. Effectively final really means the same thing as final. So they're like anonymous inner classes in the sense that local variables have to be final, which means effectively the way that they work is that they actually take a copy of the value of a local variable and then work with that. So a non-final local variable might change its value subsequently, and then what the lambda does, since it works with a copy, would be invalid. So syntactically that won't compile, but you could get around that in the same way as you can do with anonymous inner classes. Very simply, for example, by making this into a field. If you make it into a field, then that will work. But it's still a really bad idea. So here's a second reason why it's a bad idea. It's a bad idea because, in principle, and perhaps in practice, you might want to run this in parallel. So if you make this into a parallel stream, I'm not going to talk much about parallel streams today, but they underlie everything. Everything in the Stream API. If this was a parallel stream, then this wouldn't be thread safe. Because obviously, as we know, if we allow threads access to, if we don't regulate access to a variable from multiple threads, then an operation like addition, which is non-atomic, will result in data corruption. So that's not safe. So there's an alternative there, which of course you could put it into a mutual exclusion. You could apply mutual exclusion and put it into a synchronized section, but then of course you would lose the advantage of going parallel. So this code is not parallel ready. You couldn't run it in a parallel stream. But there's a bigger reason even than that for not doing this. And that reason is that the style of it is bad, and we're trying to get away from the idea that we're trying to get away from iteration, basically. So the parallel ready is a good model for code, not only because because it means that we're future-proofed. If technology improves to the point where we can run our code in parallel, but also because even at the moment, even today, we're going to get better code by, as Brian Getz says, pulling our head out of the sink he puts it more dramatically than this, but pulling our head out of the sink of iterative thinking. So the short answer is don't do that, right? So instead, what can we do? What we can do is we can use reduction. So here's the difference. Here's a graphical explanation of the difference between using an accumulator like this and using reduction. So the execution graph for this code here, which is just this, I've not used streams here, but I'm just showing how I'm comparing reduction with iteration in a more familiar setting. We're going to, I've just created an array of integers here and set each one to the value of its index. And now I'm going to add them up using an accumulator. And the evaluation graph is going like this, because we're starting with the first element and we're just adding each element successively to it. Now you can see that in principle there's no way in which you could execute this in parallel. Or if you tried, if you had different threads, they're going to each need to get exclusive access to that to the sum variable, and there's going to be a lot of contention. The lock on sum is going to get hot. So what's the alternative? How could you actually distribute this summation operation over the whole array? Well, the answer is you could use what's called reduction. I guess most people will be familiar with the idea of reduction. In general, functional programmers have been using it for decades and decades. We've got two overloads of reduction on int stream. So I'm just talking about int stream now to make things simple. But I'll go on to talk about reference values in a little while, because it's just easier in the first place to use an example we're already familiar with. So we've got two overloads here. The one I'm interested in now is this one. I'll come on to talk about the other one in a minute. So the same code that I just showed on the previous slide would look like this if we used reduction. So the reduce operation, so what we're saying is we're going to supply a stream of values. It's taken from the same array, and we're going to give this to the terminal operation reduce, which is going to take any pair of values that it's given, and any pair of values A and B, and it's going to do this to them. It's going to return that value, which is obviously the sum of them, which is where we're headed. So you could imagine two different threads, each operating on two different parts of the array. It wouldn't be very efficient, obviously. It's not sensible to have threads operating in such small sections of the array, but that's the idea. And then eventually they'll have to be combined together, and you've got the same operation again. So each pair of values is combined according to this rule, and that also goes for this as well. And actually, the order isn't necessarily determined. The operation has to work equally well, even if the evaluation, because the speed of threads is indeterminate, and you don't know how many threads you're going to have, and so on and so forth. It has to work equally well with a different execution graph, and I could draw other ones as well. Obviously, a large number of them for a big array. So the rule that means that all the different execution graphs will all result in the same value. That rule is that the operator here, this operator, has to be associative. That means that it doesn't matter how you group the operands to it; they've got to give the same result. A plus B plus C has got to give you the same result as B plus C plus A. Provided they're in the same order, it shouldn't matter how you group them. And that's a way that we have to start thinking about the operations we're going to do on our data, because this associativity rule is pretty important for creating parallel code. So overall, the picture is going to be something like this. On a larger scale, we'd imagine we're going to have if we wanted to use sum the elements of an array, which is my example here, in parallel, we could imagine on a larger scale, we'll partition the array for different threads, and then each thread will work on its own section of the array. The order in which it does the evaluation doesn't matter. And then in the end, so I've colored these differently for two different threads. And then in the end, they can be combined. So in principle, if the operations going on here are sufficiently expensive, then the idea of parallelization is that the overhead of breaking the array up into sections and then the overhead of combining them at the end is going to be offset by the saving that you'll make in performing these expensive operations in parallel. And that's the idea behind parallelization. So there's efficiency concerns here, and there's also code clarity concerns as well. The intermediate operations. So it's not. It turns out that the scenarios, the situations in which parallelization is really effective, is quite a narrow set of situations. The intermediate operations have to be quite expensive, and they have to be expensive in CPU terms. So if there's a lot of I/O in your intermediate operations, this doesn't work very well. It's quite a narrow niche of execution scenarios. But the principle of writing code that will be fit for doing this is worthwhile, because we know that niche is going to widen as time goes by. So this is reduction on primitives, and it's pretty straightforward. Now, what about reduction on reference types. Well, you could have reduction on immutable reference types without any problem. So we've got here's the API for reduction on streams of T rather than int stream or long stream, and you can see what this does is it takes something slightly different. We've got an overload like the one I just showed you for int stream here, where we were substituting addition in here. But this time we've actually got an identity as well as the binary operator. So how does that work? Well, you would say, oh right, and the example I've got here actually doesn't use this one, but uses this one, I'm afraid. So here we've got an immutable reference type. One of the very few immutable reference types in the platform libraries is big decimal. So if you wanted to add up big decimals in the same kind of way as I added up primitives, ints, a moment ago, then you could use the add operation on big decimal, and it would work in pretty much the same way. My mistake here was not in fact to use reduce here. If I wanted to use it on with this overload, which was my intention, I should have said, although this would work, I should have said the identity for addition for big integer is of course big integer of 0, because you can add adding 0 to a big integer doesn't change it in any way. There's an identity for each operation. So the identity for multiplication is 1, the identity for addition is 0, and so forth. And that's the overload that I really wanted to look at here, because what I want to go on to now is to talk about collections. And for collections, you actually have to have some kind of a start for the reduction operation, and in fact, reduction sort of does work with collections. So what you could do is you could, in order to get started, you could make the client code. The reduction operation can't create an empty collection, so the client code would have to create the empty collection. You could add a single element to it, and then the reduce operation could combine all these things together. But it's not very nice. At the end of the talk, if we survive that long, I'll show you comparison between, in a practical case, between collection and reduction, and you'll see that it's very clumsy and it doesn't really work very well at all. Reduction over an identity, which is where I was headed with this. All right, we've got it here. It's like the one I showed for IntStream here. This is the one that I was after for reference types, and here it is with big decimal. We're using the identity of big decimal 0 and big decimal add, and this works okay. This works fine for immutable objects. Here's the diagram of what it looks like of what reduction over an identity looks like for ints, with the identity being 0. So you can feed it in. So why am I talking about that? Because I'm interested in collections, and I want to think about how we would. In the end, Java's not a functional language. What we're going to do is we want to dump the values that result from stream processing into mutable collections, and that's where we're headed with this. So here's the overload that they thought, when they designed the API, they thought they were going to use for this, because they actually didn't understand the problem that I'm about to explain to you now. They said, well, what we'll do is the idea is that if we've got we'll start with an empty collection, and we'll have something that you call an accumulator. So if you want to add, this takes it's a by function on the type that we're. Sorry, I should say. Here's the identity. U represents the collection. Here's the by function is going to take a collection and a single object, and it's going to return a collection. So in other words, this adds elements to a collection one by one. It's like the add method on collection, in fact. And here's a combiner, which is a binary operator on U, and this merges two collections, right? So the idea of that is that's like the thing that happened at the bottom there. And that would be like add all on the method that we have on Java util collection. And this overload that you see here was their idea of how things were going to work. But it's useless. Actually, it shouldn't be in the API at all. It's a mistake, and it's really misleading. This is what it would look like if it worked. So you'd have you've got the accumulator, which I showed you there, which I showed you on the previous slide. It takes an element, adds it to an empty collection, and you've got and so on. So you've got all the single threads working on each of these, and then you've got the combiner at the end. Possibly several combiners, depending on how many threads you've got. So, reduction over an identity like this doesn't work at all. Why? It's really not obvious. I hope to be able to give this book away, but I won't be entirely surprised if I can't do it. I wrote a significantly large example in the book based on not understanding this, and there are other books out there that actually kept those examples in there because it's really not obvious. It wasn't obvious to the API designers, but hello, anybody there? Everything's gone. So. You don't need to see the screen to ask yourself, why? Why? It really doesn't work. I've totally lost the screen. Right, any guesses? What bad timing, what a shame. What a shame. So I'll have to figure out, now I have to figure out another question. I was so pleased with myself that I found a question to ask, a reasonably hard question to ask with a single answer. Reduction reuses the identity element. So the problem is that one thread would work with this, only one copy of an empty collection is going to be created. The whole idea of reduction is that because it depends on immutability, the assumption is it can use the same identity element in different places. But of course, if you have a reference to this thing and it's already been worked on by one thread, and then you start using it in another one, you're going to get insane answers. So reduction to collections doesn't work. Reduction over an identity doesn't work with collections. Reduction reuses the identity element, and they had to invent something else. Here's what they invented. The answer is, this kind of completes the picture of how collectors work, or nearly completes it. It's like the previous picture, but the difference is that instead of an identity element, you have a function that creates a new empty collection. So this thing's called a supplier. Right? And this supplier, which will be applied by each thread when it starts its sequential work on its data set, its segment of the collection, will produce a new empty collection each time, and everything will work okay. So these three elements here, the supplier, the accumulator, and the combiner, are what constitutes a collector. Actually, there's something else as well. Sometimes some finishing work needs to be done afterwards. The best example of that I can think of, or the most obvious example, is a collector which is in the API that combines strings together. Internally it uses a string builder to do that, of course. But what you want to get back at the end is a string. So what happens is the string builder is built up in the threads in the same way as that diagram showed. And then right at the very end, after everything's been combined together, a final operation is performed, which is to call the toString method on the string builder, and it spits out a string at the end. So really there's four elements, but these three are the ones I'm concerned with here. So that sounds really hard. And in fact, when I was writing the book, Brian Getz, who was a reviewer for the book, said, "Don't explain all this stuff to people because it'll make them think that the collector's API is really hard to use." And he's very, very keen to let you know that you don't have to do all this work. I like explaining how things work, so and he's not here anyway, so I can do what I want. And I want to do this. But he's right about one thing. It sounds hard. It actually sounds a bit harder than it is, but it still does sound hard. So it's good that we don't have to do it, because obviously, foreseeing that people wouldn't want to, they supplied a really comprehensive set of collectors in the platform libraries. So it's good that we don't have to do it. I will talk about doing it. I mean, there's increasing interest in writing your own collector. But when you first come across the Stream API, and for most ordinary development life, you don't have to create your own collectors. It's good to understand them, but what you really have to do is to know how to use the ones that they've supplied in the collectors API. And that's what I'm going to talk about now. So this is really, perhaps in some ways, the most important part of the talk, using the predefined collectors. So the predefined, you get these predefined collectors from factory methods in the collectors class. They produce standalone collectors. Well, actually, they produce lots of different collectors, not only standalone ones. You'll see what I mean by standalone and non-standalone collectors, downstream collectors in a minute or two. But the three that we're going to be interested in, I've divided them up like this because I like dividing things up. It makes them easier to remember. Framework supplied collectors that accumulate to different kinds of things. Framework supplied containers, custom collections or classification maps. So the predefined standalone collectors that are produced by the factory methods in the collectors class, which is one of these utility classes with lots of static methods in it. These static methods include toList, toSet, toMap, and joining. Joining is the one that I talked about that joins strings together. It's very nice and very flexible. It solves the problem that we've always been bothered about how do you join things together with a separator without having a separator on the end and having to take the separator off, if you did it in a loop. So it's a neat and useful thing. But obviously the ones that are important are the ones that are collecting to collections. To map and to collection will allow you to supply your own collector, your own collection to be collected to. These use very standard ones. This one collects to array list. This one collects to hash set. That one collects to hash map. And I'm going to talk more about these grouping by methods in a minute. Let's talk first of all. Oh, right, and of course I've talked about what's on the slide now. Framework provides a supplier. User provides a supplier, and this produces a classification map. So the difference between these is essentially what's the function what's the factory that's going to produce that empty collection in the first place. Here's an animation which you may think is a bit insulting, but you'll see they're quite useful in the end, of how the collector that is produced by this static method on collectors, the toSet method on collectors. Here's an example of how it works. I'm imagining that values are going to come in on the stream here. Here comes Bill, which is a person object. The collector constructs a set internally, and it puts a reference to Bill in that set, and then when another person object comes along, it puts a reference to that in there, and so forth, until the stream is exhausted. If the source of the stream, which I'm assuming was a collection that had Bill, John, and Amy in it, when it's finished, streams are for one use only. The stream is exhausted, and then the collector emits the values that it's accumulated. So in this case, a set of person comes out again. So that's sort of an insultingly simple picture of how toSet works. But you'll find that not all of them are quite that easy to imagine. For example, reading the signature of toMap is a little bit harder. What toMap requires is two functions. One of them which is going to extract the key from each value that comes in, and the other one that's going to extract the value, the corresponding value for each function, for each element that comes in. So imagine that we were going instead to collect the stream of person objects via toMap collector, which is going to map the city of each person to the name of the person. So this would look something like this. Here comes a value, and the key mapper gets city from the person object, and the value mapper gets name from the object. And now we've built an entry which is London mapped to Bill. That string Bill is the name, and so forth for the other elements. So that's how that one works. And again, when the stream is exhausted, the map is emitted with the entries in it. Of course, that isn't necessarily always going to work, just as we've said there, because sometimes what might happen is, of course, that you might get two people living in the same city. And in that case, I mean, if John also lives in Athens, then, well, you can't have obviously two values for the same key. So there's another overload of the toMap method, which you get an illegal state exception in that case. But if you want to allow for that possibility, and for the possibility of multiple values with the same key, then this further overload allows you to say what you want to have done with the two different values that occur on the key. So that this will say, well, if they happen to be the same, if they happen to have the same key, then this is what I want to have done with them. Well, we know that the values that are produced by this value mapper are going to be strings. So we might, for example, say, well, if you get two strings and both of them correspond to the same city, then we'll concatenate them together. And that's what we'll put into the map. Yes?
But it's always a good idea to use a filter before this toMap. Because in my practice, I shoot my text several times due to pointer exception. It's not so clear. The JavaDay for toMap states that the merge function will be, merge algorithm will be used, and it doesn't allow the null pointers at all.
Right. So we always potentially have a problem with nulls. So the point is, the merge function is if you have a possibility that you're going to have to that one of these things is going to be null. Let me think. One could accommodate that, but you would have to have a more complex function if that's going to be the case. So an alternative is obviously to filter the values as they come down the stream before they get to the collector. A second one is possibly to accommodate nulls in your merge function. But it's an interesting point. Thank you. So in this case, the animation will show clearly that what's going to happen now is that when we have those two values, then we're going to get both John and Amy live in Athens, and so the function will concatenate them together, and that is the result. That's going to be the result. So that's what the framework supplied collectors look like. I mean I haven't talked about toList, because toList is just the same as toSet in terms of what it does. Custom collections allow you to the ones that accumulate to custom collections. Just allow you to provide a factory for the supplier. So, for example, supposing you wanted to accumulate the elements from your stream to a tree map, then this might be what you chose to do. If you get two values with the same key, you're going to concatenate them. And by the way, we don't want to put this into an ordinary map. We want to put it into a sorted map, a navigable map, I should say, a tree map. And so I don't think is there an animation to go with this? Yeah, that's right. So that's the map factory, which is the starting point for the accumulation. You can also collect to maps. Maps are different from other kinds of collections because, of course, they don't extend the collection interface. Here, the collection interface means the fact that the collection interface is the super type for all other kinds of collections means that one other method covers everything. So we've got toCollection, and the supplier of C is just a factory for some kind of collection, and that will work with everything. So it has to be constrained. C has to be some kind of collection. And then that returns a collector. By the way, if you see the signature of collectors like this, if you see the type of collectors, then it's quite hard to decode this. A collector which has these parametric types is taking things of type T, is collecting them into a container of type C, and the thing in the middle here you usually don't care about very much. It's the intermediate type it's the type of the intermediate data structure, which is quite often the same. For the ones I've shown here, is the same as the final one. But if there's a finisher, it may be different. So, for example, it would be string builder in the case of joining. But you usually don't have to worry about that. So here's an example of collecting. Supposing we wanted to collect our person elements to a tree set, then we would collect into a collector which is produced by calling toCollection providing a tree set factory. And the last one, which I've kind of condensed myself with time, but I may have to just go over into the second session for a minute, are the classification maps. The classification maps are really the most interesting. You can do most with them. So far, this is really kind of fairly elementary, but the classification maps make it really interesting. You can do a lot of work with them. So I call these classification mappings. I don't know. I think they're probably I don't think there's a standard name for them. They're like to map, except the values that are placed in the map are lists of the elements, one list for each classification key. So for example, if we use person.getCity as a classification key, then we would get a map from city to list of person, and the list of persons would be obviously those for each city. So we could write something like this if that was what we wanted. So here's how that works in terms of the animations. The classification map here is going to it's created by the get city method on person. So Bill maps to London, and John maps to London, and Amy maps to Athens. And the way this is going to work is that it's going to create a list corresponding to. It's going to create a list of person objects corresponding to each of the value types here, the cities. And so when we get a duplicate, then it can be added, because what is being created here is a list corresponding to each one, and so the map is from city to list of person. So you might say that seems a bit arbitrary. I mean, you should say that seems a bit arbitrary. Why do we always have to get lists? Because so far everything's been really quite flexible, and there's been ways of having custom collections for everything. And of course, that is actually the case here as well. Although the default container that grouping by collects to is a list, as in this case, you can actually, of course, there's another overload that allows you to change that. So the grouping by with classifier and a downstream collector allows you to do further processing on the values that have been classified by the upstream one. This, by the way, is the reason why I'm so keen on the collectors API. It's because you can compose collectors together in this very neat way and allow them and chain them together to do lots of complicated processing. So the idea is that instead of using the classifier function to make a classifying mapping into a list, it can just be into anything defined by a downstream collector. So everything else is the same. So here what we've done is, instead of saying we want to have a map from city to a list of person, we say a set of person. And what we've done here is use this new overload, grouping by, with the same classification function, but with a collector there. ToSet creates a collector. This is the collector for putting things in a set. So we're going from. We've got the classifier, and then this is why it's called a downstream collector, because it gets streams from the upstream collector, the grouping by. So what it's going to look like now is this. I mean, it doesn't actually make a huge difference in this case, except that you see that what the values are going to be put into are whatever the downstream collector creates, not arbitrarily a list, but whatever you decide you want. Yeah. So that's how that works. And what we find is that this idea of this, by the way, is why I talked about standalone collectors, because the standalone collectors are the ones that can function as downstream, as upstream collectors. And now I'm going to show you when we get past this, because I think you probably get the idea of what's going on here. Let's just skip through this. Okay, so that's what's going to be put out from that example, and here's an example of something which is a downstream collector, mapping. I'm going to show you mapping in the last couple of minutes before lunch. I'm going to show you mapping in a peculiar context because I can make a animation of this, but I'm also going to explain why it is that you wouldn't use it normally this way. So let's suppose that what we wanted was to mapping, by the way, requires a downstream collector itself, even though it's itself a downstream collector. So what we're doing here is we're going to classify. We're going to transform. We're going to do the same thing as the map intermediate operation would do. We're going to transform each person into the city they live in, and then we're going to collect those into a set. That's what mapping does. So it does some processing, and then it passes it on to a collector. So that's what the animation looks like. And I guess this is kind of obvious here. I mean, the way it's going to work. Each one of the values that we get out of this, we're transforming each one of these things into the city property, each one of these person objects into the city property. And then what we're doing is we're putting them into a two-set collector, and it's the set that will then be emitted. But that's a kind of stupid example, because why would you do that? You might think, well, why would I do that when I could have just used the intermediate map operation on the list, on the stream, before it arrived at the collector? I mean, it would obviously make sense in this example. In this example, to simply say, well, I want to map each person into the city, and then I want to collect the cities into a set. That would make more sense, wouldn't it? Well, there's actually a very good reason for doing this, because the way we actually use the mapping collector and downstream collectors in general is what we want to do typically is we want to use them in a situation where we couldn't have done the mapping, we couldn't have done the map on the intermediate operation first. So here, for example, supposing what we want is to classify not people by city but names by city, then we're going to have to do the classification first, and then we can map each person to their name and collect them. And well, in this case, what I'm doing is I'm joining them together, but it doesn't really matter what it is. So it's when you want to do further work, when you want to do some classification, and then you want to do further work on the operation, on the values you've got afterwards. You couldn't do that work first because you would have lost the information that's needed. If you did the further work first, you'd have lost the information that might be needed by the upstream collector. So here's a picture which I couldn't animate. It's like really too much work about how that works. So here you've got the first collector, an upstream collector. Here you've got the downstream collector, which is mapping, which has its own downstream collector joining. And this composition of these collectors together is very powerful. It's really great. Okay, I've got one last slide before lunch. So often these collectors are really useful. These downstream collectors are so useful that they've provided factory methods that correspond to each one of the. I mean, I've shown you mapping, which corresponds to terminal operation, to an intermediate operation on the stream. But also there are factory methods that correspond, that give you back collectors that correspond to each one of the terminal operations as well. So we've got something like counting, for example. A counting collector does exactly the same thing as count will do as a terminal operation, but it does it as a downstream collector. Same for, and similarly for all of these other methods, MaxBy will calculate, uses a comparator for a downstream collector to give you the single largest element, in the same way as Max would do if you could apply it directly to the stream, and so on, all the way down the terminal operations. So that's a pretty fast run through of how the Collectors API works, and you probably, I mean, if you knew it already, then you'll have been drumming your fingers. But if you didn't know it, then there's probably quite a lot going on there. So after lunch, we'll spend most of the second half just trying some examples out in practice and just seeing where we can get with them. And maybe I'll get an opportunity to give away the prize. I have to think of a question that's going to be the right one now. Okay, so enjoy your lunch, and I hope to see you back afterwards.